Dear students, in continuation of our discussions on units and measurements, today we will discuss dimensions of physical quantities, dimensional formulae and dimensional equation. And we will end our today's discussions with dimensional analysis and its application. Please note down all the important points discussed here, as these will help you in learning future discussions. In this section, we will study about dimensions of physical quantities. As we all know, there are several physical quantities in the physical world. These physical quantities are like velocity, speed, acceleration, pressure, force, momentum, energy, etc. etc. The nature of a physical quantity is described by its dimensions. We also know that there are seven basic fundamental quantities. The basic quantities are the length, the mass, the time, the electric current, thermodynamic temperature, luminous intensity, and amount of substance. All the physical quantities represented by derived units can be expressed in terms of some combination. Note, some combination of seven fundamental base quantities. We shall call these base quantities as seven dimensions. That is, there are seven dimensions of physical world. These seven dimensions are written or denoted within square brackets. Thus, the length has dimension capital L within square bracket. Mass is denoted by capital M within square brackets. Time is denoted by capital T within square bracket. Electric current is denoted by capital A within square brackets. Thermodynamic temperature is denoted by capital K within square bracket. Luminous intensity CD, candela CD within square brackets. CD is in small letters. And amount of substance, mole, is represented by MOL, small letters, in small letters within square bracket. I will read once again. The length has dimension capital L. Mass is denoted by capital M. Time capital T. Electric current capital A. Thermodynamic temperature capital K. Luminous intensity small cd, and the amount of substance mole within square brackets. Please note, all these dimensions, seven dimensions, are written within square brackets. And these are denoted, some are by capital letters, like length is capital letter, mass is capital M, time is capital T, electric current is capital A, thermodynamic temperature Kelvin is capital K, whereas luminous intensity CD in small letters and substance mole in small letters. The dimensions of a physical quantity are the powers. So the definition of dimension is the dimensions of a physical quantity are the powers. It is the power or the exponents to which the base quantities are raised to represent that quantity. Let us understand what are these powers. For example, in mechanics, all physical quantities can be written in terms of dimensions L, M and T. That is, out of 7 dimensions, we use only 3 dimensions. That is length, mass and time in mechanics. Example number 1. Volume is equal to, we know, is equal to length into breadth into height. So it has, length has dimension capital L, breadth also capital L and height also capital L. So there are 3 L's, L into L into L. It can be written as L cube or L cube or L cube within square brackets as shown in the slide. Volume is independent of mass and time. So, volume has no dimension in mass and 0 dimension in time. Hence, it has 0 dimensions in mass and written as capital M to the power of 0 and 0 dimensions in time, that is t to the power of 0, and 3 dimensions in length, that is L cube. Example number 2, force. Force by definition is force is equal to mass into acceleration. That can be written as mass into acceleration is velocity over time. Velocity itself is length over time. That is equal to mass into length divide into 1 over time into time. So that is mass into L. Mass is capital M, length is capital L and time into time is t square. That is equal to M into L and t to the power of minus 2. T to the power of minus 2 is because t square in the previous formula is equation term is t square. When t square goes to numerator, it is t to the power of minus 2. Thus, the dimensions of force are mass into L, M into L into t to the power of minus 2, all written within independent brackets. It has 1 in mass, 1 in length and minus 2 in time. Next, we will take up the section 2.9, Dimensional Formulae and Dimensional Equations. The expression which shows how and which of the base quantities represent the dimensions of a physical quantity is called dimensional formula of the given physical quantity. So these expressions are represent the dimensions of the physical quantity. For example, volume has m to the no mass and no time, only length. It has got dimension in L, that is L cube, length into breadth into height, so it is L cube. Similarly, speed or velocity is defined as distance over time. Distance is L and time is t. Therefore, it is L divided by t to the power of minus 1, but it has no mass. So, we have to write m is 0, L is 1 and t is t to the power of minus 1. An equation obtained by equating physical quantity with its dimensional formula is called the dimensional equations of a physical quantity. Thus, the dimensional equations are the equations which represent dimensions of a physical quantity in terms of base quantities. That is, there are 7 base quantities and we have to express the dimensional equations in these. Volume, for example, again repeatedly, volume is equal to m to the power of 0, that means no mass, L cube, it has got 3 dimensions in length into breadth into height and no dimension in t to the power of 0. Velocity is distance over time. So m is 0, L is 1 and denominator t, that is m0, L1 and t to the power of minus 1. Force is m into a, therefore it has got mass. Mass into acceleration. Mass is m, m as 1, L is 1 and t to the power of minus 2. Lt to the power minus 2 is for acceleration. Density rho is equal to, it has got mass over volume. Mass m is 1, volume is divided by denominator is minus 3 and no dimensions in t. The dimensional equations can be obtained from equation representing the relations between physical quantities. Let us take some example. The following quantities are dimensionless quantities: pure numbers, ratios, exponential function, that is e to the power of x, logarithmic function log x, trigonometric function like sin theta, sin x, cos x and tan x. Important dimensions of physical quantities. The table 1 gives you about 28 important parameters or physical quantities like velocity, speed, acceleration, momentum. All these you are going to study in subsequent chapters, and their units are given in column number 3 and their dimensions in column number 4. You just go through, and when you complete the discussions in subsequent chapters, you can come back to this. Similarly, heat. The chapter heat, there are about 15 parameters, and it's like temperature, heat, specific heat, thermal capacity, etc., etc. And these are physical quantities are given units, and physical quantities, their dimensions are given here. So please just glance and remember that the different dimensions of physical quantities. Quantities having some same dimensions. Some dimensions are common to different physical quantity, like dimension for time, that is frequency, angular frequency, etc. Frequency does not have mass, so m to the power of 0. It does not have a length, so L to the power of 0, and it is 1 over t is time t to the power of minus 1. So such there are about 14 dimensions which are common to some of the physical quantities. So these quantities are given in third column. So these have same dimensions, and you just go through and remember. Dimensional analysis and its application. Dimensional analysis helps us in deducing certain relations among different physical quantities. Checking the derivation, accuracy and dimensional consistency or homogeneity of various mathematical expressions are checked using dimensional analysis. Applications of dimensional analysis. First application is to find the unit of physical quantity in a given system. Second application is to find the dimensions of physical constant or coefficient. To convert a physical quantity from one system to another system. And fourth application is to check the dimensional correctness of a given physical relation. This is based on principle of homogeneity. According to this principle, the dimensions of each term of both sides of equation must be same. So to check the correctness, The left hand side dimensions and right hand side dimensions should be same. To derive new relations, we use dimensional analysis for deriving new applications. Limitations of dimensional analysis. If the dimensions are given, physical quantity may not be unique. As we have seen in a previous table, some of the dimensions are common for many physical quantities. Numerical constants have no dimensions, cannot be deduced by the methods of dimensions. The methods of dimensions cannot be used to derive relations other than product of power functions. For example, S is equal to ut plus half a t square. We cannot cannot use the product function. We can use only for powers of the product. We cannot be used to derive relations. Similarly, y is equal to a sin. So sin omega t does not have dimensions. Because of this symbol ut and half a t square we cannot determine. The methods of dimensions cannot be applied to derive formula consisting of more than 3 physical quantities. So only 3 physical quantities we can cross check. Checking the dimensional consistency of equations. The magnitudes of physical quantities, that is, like for example, length, mass, length and time, may be added together or subtracted from one another if and only if they have same dimensions. In other words, we can add or subtract similar physical quantities. Thus, a velocity cannot be added to a force. Velocity can be added to velocity only, and force can be added to force only. An electric current cannot be subtracted from thermodynamic temperature. This simple principle is called the principle of homogeneity of dimensions in an equation. This is useful in checking the correctness of an equation. Example. Let us take an example. Work done we know is equal to force into displacement. Dimensions of work done are ml square t to the power of minus 2. And force is ml t to the power of minus 2 and displacement is length only. So m to the power of 0, l t to the power of 0. Therefore, simplifying we get m plus m0 is m, l plus l is l square, t to the power of minus 2 plus t0 is t to the power of minus 2. Hence, left hand side is equal to right hand side. Thus, the dimensional consistency is verified. Example number 2. Now consider equation S is equal to ut plus half at square. So S is a distance and u into t also should have the same dimensions and half at square should also have the same dimensions. So let us take only S is equal to ut. So S is, we know, only length, that is distance is m to the power of 0, l to the power of 1, t to the power of 0, that is equal to u is mass, m is 0, mass into length is l and mass is and t to the power of minus 1. U, these are the dimensions of u and dimensions of t are m to the power of 0, l to the power of 0 into t. That is equal to, you see, left hand side is m to the power of 0, l to the power of 1, t to the power of 0 equals, if you add m0 plus m0 is m0, l1, l to the power of 1 and l to the power of 0 is l, and t to the power of minus 1 and t to the power of 1 is t to the power of 0. Hence left hand side is equal to right hand side. Similarly, we can verify the dimensions of half at square. Half does not have any dimensions. We have to verify for at square. Deducing relations among physical quantities. The method of dimensions can be used to deduce relation among physical quantities. For this, we should know the dependence of physical quantity on other quantities up to three physical quantities. So the limitation of dimensional analysis is only it is limited to three physical quantities or linearly independent variables. Considered it as a product type of dependence. Example, a simple pendulum time period t depends on mass, length and gravity. It is given by the relation T is proportional to m to the power of A mass, L to the power of B and G to the power of C. We can find out the powers of mass, length and gravity. So let it be equal to K into m to the power of A, L to the power of B and G to the power of C. Here K is a dimensionless, A, B, C are exponents. Considering dimensions on both sides, we get time is m0, m to the power of 0, L to the power of 0, T to the power of 1. K does not have any dimensions. Mass is m to the power of 1 into A and a length is L to the power of 1 to the power of B and gravitational force is G is L1 gravitation L1 t to the power of minus 2. Therefore, that is equal to m to the power of A, L to the power of B plus C. Here B and here it is CB plus C, t to the power of minus 2C. Therefore, equating dimensions on both sides, we get A is equal to 0, B plus C is equal to 0 and minus 2C is equal to 1. So these are put here and we have find the value of A equals C, B equals half and C is equal to minus half. Substituting the values of A, B and C, we get the equation T is equal to K into m to the power of 0 because A is 0 and L to the power of half because B is 1 by 2 and G is equal to minus half. So therefore, we can rewrite this equation as length of pendulum, period of pendulum as T is equal to K into square root of m is 0, we can eliminate. L square root of means L to the power of half divided by G. This is in denominator. Hence, minus half goes to denominator. Hence, equation for simple pendulum is derived. Example number 9. Check whether the given equation mv square is equal to half mgh is dimensionally correct. Here m is the mass of the body, v is the velocity and g is the acceleration due to gravity and h is the height. Answer. The dimensions of left hand side, that is mv square is m lt to the power minus 1 whole square. That is m is the mass m and lt to the power of minus 1 is the dimensions of velocity, whole square is given. So it is simplifying, we get m into L square t to the power of minus 2. On the right hand, that is equal to m square t to the power of minus 2. Dimensions of right hand side are, that is right hand side is half mgf. Half has no dimensions, mass has m, capital M, G has Lt to the power of minus 2, that is acceleration. H is L once again. Therefore, it becomes ml into t to the power of minus 2. So, left hand side is equal to right hand side. Hence, the equation is dimensionally correct. Example number 10. The SI unit of energy is given by J is equal to kg meter square per second square. That of a speed v is ms to the power minus 1 and of acceleration is ms to the power of minus 2. Which of the formulae of kinetic energy given below can you rule out on the basis of dimensional argument? M stands for mass of the body. K is equal to m square v cube. These are the given. K is equal to half mv square. K is equal to ma. K is equal to 3 divided by 16 mv square. K is equal to half mv square plus ma. Answer is dimensions of K are m l square t to the power of minus 2. For A, dimensions of K are ml square t to the power of minus 2. So, dimensions of right hand side for A, right hand side is m square, L is L t to the power minus 1. So L cube is this one. So it is ruled out. So left hand side is not equal to right hand side. Dimensions of right hand side in case number 2 is K, right hand side is M L square t to the power of minus 2. This is correct. K is equal to half mv square is correct. So K is equal to M into L to the power of T ML t to the power of minus 2. So it is L, right hand side is single L, left hand side is L square. So it is not correct. In the fourth case, that is D, K is equal to 3 by 16 mv square. M is capital M and velocity is L square t to the power of minus 2. This is correct. E is K is equal to half mv square plus ma. No proper dimension due to addition. This addition does not have two different dimensions. Ma is force, mv square is half mv square is energy. So let us summarize. With this, let us summarize units and measurements. Physics is a quantitative science based on measurement of physical quantities. Certain physical quantities have been chosen as fundamental or base units such as length, mass, time, electric current, thermodynamic temperature, amount of substance and luminous intensity. Each base quantity is defined in terms of certain basic arbitrarily chosen but properly standardized reference standard called unit, such as meter, kilogram, second, ampere, Kelvin, mole, and candela. These units for the fundamental or base units are called fundamental base units. Other physical quantities derived from the base quantities can be expressed as combination of base units are called derived units. A complete set of units, both fundamental and derived unit, is called system of units. The international system of base on 7 base units is internationally accepted unit system and widely used throughout the world. The SI units are used in physical measurements for both base quantities and derived quantities obtained from them. Certain derived units are expressed by means of SI units with special names such as joule, Newton, watt, etc. The SI units have well-defined internationally accepted unit symbols such as M for meter, kg for kilogram, S for second, capital A for ampere, and capital N for Newton. Physical measurements are usually expressed for small and large quantities in scientific notation with powers of 10. Scientific notations and prefixes are used to simplify measurement notations and numerical computation, giving indication to the precision of the numbers. Certain general rules and guidelines must be followed for using notations for physical quantities and standard symbols for SI unit, some other units, and SI prefixes for expressing properly the physical quantities and measurements. In computing any physical quantity, the unit of derived quantities involved in the relationships are treated as though they were algebraic quantities till the desired units are obtained. Direct and indirect methods can be used for measurement of physical quantities. In measured quantities, while expressing the result, the accuracy and precision of measuring instrument along with errors in measurement should be taken into account. In measured and computed quantities, proper significant figures only should be retained. Rules for determining the number of significant figures, carrying out the arithmetic operations with them, and rounding off the uncertain digits must be followed. The dimensions of base quantities and combination of these dimensions describe the nature of physical quantities. Dimensional analysis can be used to check the dimensional consistency of equations, deducing relations among the physical quantities, etc. A dimensionally consistent equation need not be actually an exact or correct equation, but a dimensionally wrong or inconsistent equation must be wrong. With this, we come to the conclusion of chapter number 2, that is units and measurements. Next lecture will be on motion in straight line. Till then, goodbye.